Hello and welcome to Question Time at Padakshep with Dr. Somak Raychaudhury. Padakshep is a non-profit organization aiming at betterment of underprivileged students from West Bengal, India. To know more about Padakshep, please visit our website, which is www.padakshep.org. Question Time is a series of online events broadcast via Google Hangout, where we interact with eminent people of our society to learn more from them. If you want to see our past events, please visit our blog, which is the blog at padakshep.org. Today, it is our great pleasure to have Dr. Somak Raychaudhury, who is present the head of the physics department at Presidency University, and have been a professor at University of Birmingham. He ranked second in Madhyamik and Uच्च Madhyamik exam before joining to Presidency College to complete his undergraduate with honors in physics. He then moved to Trinity College, Oxford, to complete his BA degree. He was awarded the prestigious Isaac Newton Studentship to pursue his PhD in astrophysics from University of Cambridge. He completed his PhD under the supervision of Donald Lyden Bell. Also, he was a recipient of Smith's Prize in 1988. Welcome, Dr. Raychaudhury. Welcome to Question Time.
My pleasure.
So today, the episode we have divided into two parts. On the first part, we will ask you about some general questions about your student life. And then the second half, we will ask more particular question on astrophysics. So let's start the first part. So you are a brilliant student and you stood second in, you ranked second in both Madhyamik and Uच्च Madhyamik examination. So we want to know why you took physics as your career. What motivated you to choose physics as your career?
Well, clearly I was not alone, because if you go back to the time, out of the first 20 rankers in higher secondary exam, 6 joined Presidency Physics. So
Okay.
clearly I wasn't alone. But I mean, there's a deeper question here. I mean, I think there was no point in my life when I thought that I would do anything other than study a pedagogic subject at university rather than a professional career, take up a professional career. And that's because, you know, I wanted to be an academic. Now,
Okay.
I think a lot of people, I mean, I have nothing against, you know, people going to engineering and medical or law careers, because these are very, very rewarding professions. But I think a lot of people are pressured into taking up technical or professional careers.
Especially at this moment.
Pressured into these lines by their parents, by their peers, and also by the fear of not getting a job that can sustain them later in life. Somehow I did not have any of these fears, partly because my family was very supportive, and also there were a lot of academics in my family. My father is an academic, and I think a lot of people think of an academic line to be scary because they don't see role models in front of them, right?
Yes.
If you see people around you who are successful academics, who are able to earn enough money to you know, feed themselves and their families, then you know that you know, it's going to be a viable a career. And I do remember sitting for the engineering entrance tests, the IIT tests, etc. That was partly because I felt that I had to sit for those tests. See, I got pressured into that too, because I felt that I was pressured into sitting for those tests, because if I did not sit for those tests, people will say that I did not get into an IIT, and that is why I went to Presidency College, right? So I had to show people that I could get into an IIT. And I think a lot of people do that, and even after the entrance test, they go into their you know, their respective professional careers, and somewhere in the middle of life, often they come back to academia.
Yeah. So if I say that at this moment, when I passed higher secondary examination, a lot of the students just went to higher secondary, went to the engineering and medical, not to the basic science. So what will be your message, especially towards the parents? Because I believe somehow students are pressurized by their parents to choose engineering as their future profession, and they are not given the freedom to choose their own profession. So what will be your message if a student wants to choose physics as his career and his parents doesn't allow him to do so?
I think the message, overriding messages that I've seen, of course, as in my role as a college professor, I've seen countless students being pressurized or into various careers where they really have no interest. And I think my overriding message is that if you go for a career, which essentially is your life from now on,
yes,
and it's a career where your heart doesn't lie, then you're going to have a very difficult life. And so if the parents are pressuring kids to go into a career where they naturally don't fit, then they are actually essentially pushing their kids into careers where they're doomed for life because they will not like the things they do.
exactly.
Now, I have many, many friends who are very happy in engineering or medical careers. And clearly, by the age of 18, most of them know that that's what they want to do.
Okay.
But a lot of people don't. And thus, I think going into a very general university education is often better for them, because then they leave the choice till later. You can go into, say, doing physics or mathematics or a general subject and then go into a technical line later on. I know of many people who have done that. Many people have gone to study history and political science, gone into law after that, or going into physics and then gone done engineering by doing applied physics and electronics after that. So I think going into a general line is actually a very good choice, because that keeps options open. Once you've gone into mechanical engineering, you have chosen a profession. Exactly. And it's very difficult to come out of a specialized. Having said that, I know a lot of examples where people have eventually found what they want to do. I mean, my year, the person who stood second in the All India IIT exam, entrance exam, went in to do electronics in IIT Kanpur. He's now a professor of Sanskrit literature.
Okay.
Right.
Interesting.
So clearly he found his way. Okay. He went through his engineering degree and then he changed his career. But he didn't need to do that electronics degree, right? So he spent those years at IIT Kanpur wasting his time.
Exactly.
And that's because his parents pressured him to do what he wanted to do. So that's the clear message. The parents, can pressure students to go into educational lines, but in the end, it's the person who is doing the degree.
Yes.
He's going to have to choose.
Yeah. So rather than giving a decision, giving them a general advice and general counseling and what are the opportunities, I think that should the parents do, other than just giving the decision. They should give just the advice, right? And,
yeah, absolutely. And then make it easy for people. Like, I think my parents were excellent in that, and then they made it very easy for me to make the decision, because they supported me in whatever I wanted to do. And very clear where I was going to go.
Okay. And now, sir, what was your first tryst with astrophysics? Because you choose a career in astrophysics. Was just after higher secondary you choose you were going to do physics, or
That's actually a very interesting story. I mean, I in my first year I got the Jagadish Bose National Science Talent Search Award. Is this working? And then and as part of the award, the students, the awardees, were taken around India to visit various research institutions. And so in my second year actually, my first trip, I landed up at the Raman Research Institute, Bangalore, where our entire a bunch of students were treated to some really, really interesting talks by various scientists, and we were shown around the Uti telescope, for example. And there were a couple of particular scientists. There was Radhakrishnan, who's C.V. Raman's son, who's then the director of the Raman Institute. And his team gave some really interesting talks on astrophysics. And I mean, I think that one evening changed my life, of listening to some really interesting astrophysics talks. And I wrote to them saying that I wanted to work with them. And the next summer vacation, I went and worked with them while still an undergraduate. And that kind of stuff wasn't very common then. Now actually a lot of undergraduates get exposure to research. We never had that opportunity, but I was very fortunate to get it. And so those kinds of things, contacts with single people can change your life. Somebody can open a certain door for you, and I'm very lucky that door was opened for me.
Welcome to question time once again. We are extremely sorry for the technical difficulties, but we start the episode once again. So we have already asked Professor Raychaudhury 2 questions, so we'll start with our third question. So, sir, you a long part of your educational and professional career has been spent in UK. So how do you compare the education system prevalent in West Bengal that time with contemporary education system in Oxford or Cambridge? And what's your opinion about the present scenario about the education system in UK and West Bengal?
Well, the education system in West Bengal, particularly in India in general, hasn't changed much. I think the main difference is an Indian policy that was taken after independence, where in the 50s the government decided to separate research and undergraduate education, which I think was a big mistake. I think at that point, I think the government decided the number of scientific researchers is very small. They needed to be protected in research institutes, and so that they didn't get too much teaching. They were taken out of the universities, and that is not, I mean, I think the government thought that they would change it in a few years. That never happened. And as a result, Indian universities in general were landed with teachers who did not do research. Yes. And research institutes did not get students. And as a result, research institutes slowly started losing the best Indian students because the students went through the colleges. They didn't see any inspired research going on. They didn't witness anything. They just went abroad. And yes. And the people who taught the undergraduates, and still don't do research, so they don't keep up with the cutting edge of science and other subjects. And then what happens is that they just teach what they were taught themselves. And so that perpetuates. And as a result, things don't get updated. I think the crucial thing that you can see in universities in the West, in Europe, and in America, is that people who are teaching at universities predominantly do research. Not all of them do, but mostly they do. And as a result, they are aware of what's going on in the subject. They update their teaching. Mm-hmm. They know whether things have moved on, whether things have become irrelevant and stuff like that. And that never happens. I think the quality of undergraduate teaching in India and in West Bengal has always been very good. And you can see that everywhere, in physics research in particular, you see people from West Bengal everywhere in the world. Go elsewhere in India, the research students in physics are all from West Bengal. People know that. Yes. I mean, once the Tata Institute, my colleagues in Tata Institute tell me that over the last 10, 15 years, 75% of all physics research students have been from West Bengal. And that's not a surprise to me because the undergraduate education is very good. I mean, I can tell you that I went from Presidency to Oxford to do a second undergraduate degree. I found that the undergraduate teaching at Presidency was far better than in Oxford. Far, far better. And when I went to Oxford, I was surrounded by very, very eminent scientists, and I learned a lot from them. But the basic undergraduate teaching that I received at Presidency College is absolutely unparalleled. And I think I can't say that quality of teaching exists now. Yeah. Because the people who taught us of the caliber of Somak Raychaudhury, etc. I mean, people like that were dedicated teachers, but they were also researchers. They were doing research on their own time. They were teaching 20 hours a week, but also doing their research. I mean, Amol Babu was one of the best relativists ever. Yeah. And now what has happened in most Indian universities, particularly in West Bengal, is that research is completely discouraged. And those people who were the famous researchers who also taught have really gone out of the system. And one of the problems we have at Presidency University now, where I am trying to set up this department, is that the people who used to teach were very good, but they were forced to teach 20-25 hours a week. They could not do any research.
Yes.
And as a result, compared to places like ICERs or IITs, they're updating their own education. Their space to think about how to teach in a new way was just not there. And I think that is one big incentive to bring in a new way of dealing with education, not just research, but also giving teachers a chance to update their reading, their studies, because these subjects move very fast. Physics moves very fast.
Yes, yes.
So if you force a teacher to teach what they learned when they were students,
yes,
is not going to work, because things have moved on. So for example, if you see in universities in the West, university teachers get sabbatical leave.
yes.
They get a chance to do research and also to update their teaching. And the kind of opportunities given to Indian and particularly West Bengal college teachers, where they go through various orientation courses once in a while, is not just enough. It might be enough in certain subjects. In science subjects, is not enough.
So, so that naturally gives the question that you have been a professor in Birmingham University for a long time. Then what made you come to presidency? Is it just a call of alma mater or something else that you took a job in presidency value? What is your motivation?
I think, I mean, that it's a there's no straightforward answer to that. I mean, I think it is to some extent an idealistic move. I mean, clearly I'm not gaining it financially by coming from Birmingham to presidency. Also, when the chance came of when the offer was made to me, my first reaction was absolutely not. It's impossible. Partly because I was in the middle of of building an academic career in Birmingham, but also my son is in class 8. My wife has not lived in India, except for the time we lived in Pune. She's from America, and whether we could actually move to Kolkata and set up a new life there was kind of out of the question. And then when I looked at the way presidency is being formulated, I thought this was a unique opportunity. Unique opportunity in the sense that it's an opportunity that comes very rarely in anybody's life, where a university is being made out of an institution which has a long heritage,
yes,
a wonderful heritage. Everybody knows about the institution, and there is a lot of goodwill surrounding it. And the opportunity is being given to build something almost from scratch.
yeah.
Right? If you go to another university and try making a department there, you always have a lot of institutional history, and it is very difficult to overcome all that and set up something new. Here in presidency, it's an institution being completely redefined, and the mandate is being given to the new people who are coming in to set up a new kind of institution, and to actually have something like. So when I actually decided to come back to India, I was also given an offer to become the director of another big institute in somewhere else in India, in southern India. And people were asking me whether I would actually go and lead another institution, which actually would have given me a salary, I don't know, twice what I get in presidency. But that's not the issue. The issue was the opportunity that of rebuilding presidency is unique, and it might work, it might not. There are many reasons for us to believe that it might not work, but somebody has to try it. And I'm very happy that when I arrived, I see a lot of people there working very hard to make this thing happen. I'm still not sure really that it's going to work, partly because not many people at the senior level are making a venture of coming into work. Only one or two people can do it. At the junior level, at the assistant professor, associate professor level, we've had some really good people. So of the 220 people that will become the faculty of presidency, now 80 people have been appointed.
Yes.
At the senior level, a few people have been appointed who have actually come from various other successful institutions to take up professorial positions. But it is really at the junior level that really a lot of very good people are coming in all subjects. And that is very encouraging. I think what needs to happen is that more people need to come from institutions where they have experienced this whole thing about doing research and teaching together. And come to presidency in senior positions, and only then it would work. I think that it is still at a level where things can go wrong. And that's because there's not enough money there. There's not enough sheer manpower to make the whole project happen. But I think it's an extremely challenging job, and I'm really enjoying it, I have to say. But
we also believe, and we also hope, we pray that we rebuild precedents, and we'll bring back the ages of 1920s where there was Jagdish.
No, the thing is, you can see that there is so much goodwill around us. Everywhere people tell us, oh gosh, this is something everybody wants this thing to happen. Not just the students. The students are part of the system. We all are trying to make this happen. But people outside the college, they all want this to happen. But they also realize that it is an institution that had really gone to pieces, not because of the people involved, but because of the system. The system allowed Presidency College. It's not Presidency College, but I think higher education in general in West Bengal had deteriorated quite a lot. And I think this is the time when we have to rebuild it. And I'm very happy. It's not just Presidency, but other institutions are coming up in a big way. The Ramkrish Mission University is fantastic the way it's moving. St. Xavier's will become a full university soon, and it's actually moving in a very good way. And you can't have one institution working alone. It's the network that has to work. Jadavpur is making a huge effort in going forward, and I think I'm very happy about the way things are moving.
Okay. So then, sir, we received a question about the undergraduate teaching, which he was explaining to us. We received a question from Arpan Kundu, who is at present a third-year student in presidency. He's asking that in undergraduate studies, being formative part of one's education, don't you think that it should involve the flavor of current research, and it should be incorporated in the curricula of our research institutes like IUCA, TIFA, HRI, etc.? And this is the first question. And the second question is that should there be any compulsion in taking of subjects? For example, if a student wants to skip electronics and wants to take a GR course in his undergraduate, shouldn't he be given that freedom to take that course? In other words,
yeah. Okay. Go ahead. Finish your
aren't we spoiling many enthusiastic mind by giving them some compulsory subjects?
Yeah, I completely agree with Arpan here. I think he's taken the words out of my mouth. First of all, the question of undergraduate research is absolutely essential. That is one of the things I said in my earlier question, was that not only do teachers need to be involved in research, but the students have to have some flavor. Otherwise, why would they want to go into a research career? When you asked me why I had gone into astrophysics, I said the same thing. I was very lucky that I was actually I came into contact with people who were doing active research, and they could infuse the excitement of research within me. Otherwise, so I think it is very important. It is not clear that a good student who's good on paper, who does very good exams, is going to be successful in research. So research has to be introduced in the undergraduate career for two reasons. One is to make sure people get interested in research. And secondly, people get a flavor of research to figure out whether they're good at it or not. You might find that somebody who has a very low first division in exams will be excellent in research, where somebody who's the topper in class will have absolutely no acumen for research. And they will not know They will not know that that is true till they actually do it. And so a lot of people go into PhD courses and they fail, which is a waste of time. They have to drop out in the middle of their PhD courses because they thought that they were very good at the subject, but they're not. I mean, not subject meaning in terms of research. So research has to be brought in. And there is also the whole question of productivity. There is so much research that can be done, even by undergraduates who have a basic training in the basics of the subject, that I don't see why they should not be involved. This research needs manpower. There is only a small number of people who do research in a particular subject. Opening research up to undergraduates just opens up a lot of a lot of resources for both teachers as well as the students. So that is very important, and that's going to happen. So the way we are going to now restructure the university's core syllabus is that we are going to bring in research at every stage.
Okay.
We've decided that, and we're going to make the presidency syllabus quite exemplary, so that other universities can see and follow us really. I'm going. We are planning it in a big way so that all subjects will update their syllabi to bring in various things, and also the question of optionality. The optionality question is very, very important. Of course, there are certain things that everybody must learn. Say in physics, you cannot have an option on learning mathematical physics or quantum mechanics or electromagnetism or basic subjects. But once you get to a stage where you go to the more specialized subjects like electronics, for example, I strongly believe that electronics is not core physics. But in most West Bengal universities, not Indian universities, West Bengal universities, electronics is taught as if it's part of the absolute core of physics. Every year there are 2-3 courses of electronics. The labs are full of electronics. Okay, it's not just electronics, but I'm taking that as an example. There are various other subjects that can be optional, and it needs to be optional. And also, I think the general basis needs to be wider. This whole question of subsidiary subjects, past subjects, etc., that people have to take against their will, needs to be also made very diffuse, so that people can pick and choose individual courses, not subjects. So right now in most universities, what you do is you do an honors course, and then you have 2 past subjects which you have to take, and then you have to learn everything from those subjects. And I don't think that is a good model. I think the choice should be, if I want to take 1 course in statistics, 1 course in mathematics, 1 course in history, 1 course in philosophy, I should be able to do that as long as I actually do some courses other than my core subject, so that I have a broad education. This kind of the liberal arts model or the liberal science model that the US universities have is actually very good. And I think Indian students would respond to that very well. Yes. I think this whole regimentation of everything being compulsory in an undergraduate education has to go. And Orpon is right, but I think Orpon will probably not get the benefit of our changing the syllabus because he's already going out. But clearly he knows what his junior students really want. And I think we're going to slowly change that.
Yeah, I think this kind of structure will be very, very good, because when we did our undergraduate from West Bengal, there are several courses we just read because we have to pass. We have to get a pass marks.
Exactly.
And that was kind of irritating, and it takes just a lot of fruitful time because there was many good subjects. And one of the things I have found is that the quantum mechanics and relativity is taught very little in the undergraduate, which is absolutely core thing in the undergraduate physics.
I mean, you have to start physics first year with relativity and quantum mechanics and thermodynamics. These things are kept for later years, and you learn absolutely meaningless stuff in the first year, which should be either in this high school courses or not there at all. Right?
Yes. So yeah, I think what the thing you and your group is trying to do in presidency will be very, very good for the future students. So, sir, there is another question in the education system in India or in West Bengal. The question is from Somak Raychaudhury, who is a postdoctoral fellow at University of Zurich. He asks the following question: that our students severely suffers from lack of uniformity in the syllabus, which differs from university to university. And also due to lack of infrastructure and good teacher, they lag behind the international standard, which have already mentioned. But can't we have lectures by good professors and lecturers which are videotaped, and we can make their lecture notes online? And how much of these things are possible in this current scenario? How much will this help to reduce the lack of uniformity?
I think that has to happen. I mean, this is the way education is going everywhere. Of course, you don't need to, every university doesn't need to have this kind of program, because distance learning on the web is there everywhere, right? You can actually, sign up for the MIT, Harvard online courses.
Yes,
you can sign up for things online. Or, I mean, these things are already there.
Mm-hmm.
The Khan Academy courses or whatever. So that material, can be used and reused in many ways.
Mm-hmm.
I think eventually this whole notion of core courses being all recorded and available to students is going to happen, will have to happen. The thing that needs to be done is translations of these things in various regional languages needs to be done, right? That is not there. So somebody who wants to study, for example, physics in Bangla cannot get enough online resources. But somebody who wants to study in English actually can now. If you go on YouTube and look at the various courses on the various online resources, they can. I think eventually universities will also have to link up by Google Hangout like we're doing now, or video conferencing, and actually share courses. I think that is also a way we can both enhance the learning for our students, but also reduce the load on individual professors so that they can do useful stuff, right? There's so much repetition. And so, I can see universities getting together and said, okay, you have a very good quantum mechanics teacher and I have a very good statistical mechanics teacher. Let's just collaborate.
Yes, yes.
And have virtual classrooms. And I mean, India has the resources already to have virtual classrooms. Most universities have these. I don't see why they can't make any use for it. And I think this will happen. And to then, make these things available to the population outside the major cities is going to be a challenge.
Yes.
And also the challenge will be to do them in the vernacular languages.
So, sir, at this moment, I will just make two comments. Firstly, as Padakshep is trying to do a similar thing, we have recently started an open teaching project, which is basically trying to build up good study materials for higher secondary exams, not for undergraduate exams. And because we have seen that people are not getting very good study materials, and even if they're getting it in the cost of a big money, which sometimes they don't have. So we are trying to do that, and I will request you that if you have some advice or some notes or anything.
Absolutely, this is a fantastic job that you've taken up.
And the second thing is that it's a question that said, for 11 and 12, we strongly believe that education should be in Bengali, and we are trying to build up notes in Bengali. But while we moved into undergraduate education and we are focusing towards overall research, do you think that is it worth to build up notes in Bengali, or is it be helpful to teach people and to help people to study in English? So for undergraduates, do you think that whether mother tongue should be a course of medium of education, or
No, I'm not saying that. Yeah, you're absolutely right. I'm not saying that, because in the end, what will happen is that somebody who wants to go into higher education will have to network with people, outside West Bengal. I mean, you cannot just remain in West Bengal, and so having a common language helps. Yes. But having said that, somebody who has studied in the vernacular from class 1 to class 12 suddenly cannot make the change going into university to a different language. So I think helping people to make the transition of being able to read these textbooks in English and also to be able to communicate the science in English is important. It is also important to see that people are not put off going into academia because they think it would be too hard for them to do things exclusively in English.
Yes.
And so having the course material available in Bengali, I mean, you can give a course in Bengali using the English terms,
exactly,
but actually talk in Bengali. right?
Yes.
And you can have, I mean, they're excellent books. I mean, just look at what Bangladesh has done. Bangladesh has translated every single possible textbook that you can get in Bengali. They're available. They have Rezni Khalid in Bangla. You can do the problems in Bangla. And so people are doing that. But you have the English textbooks there as well. And so when you're going into university, you can read the English textbooks, but things are explained to you in your own language. And that is what you need.
Yeah, so we need an education system that gives kind of a smooth transition between the mother tongue to the English language, and that should happen smoothly so that people don't feel English is a very big barrier in their way of doing good research or good physics. Okay, that I think that you tried to convey, right? This
Yes, absolutely.
Yes. So let's go to our second episode, second part of the interview, which actually is on astrophysics. It's big technical questions. So, sir, your PhD thesis is on gravity, galaxies, and great attractor survey. So we are all familiar with the term galaxies, but we would like to know. Yeah, Arnab wants to ask a question. Yes, please.
Oh, sorry. I was just thinking that if we can request Dr. Somak Raychaudhury to videotape his lectures in Presidency University, and then we can upload it.
If the technology is available, I don't have any problem with it. I think already what's happening is that you know that in Presidency we started a physics colloquium series.
Yeah.
And I've been inviting very eminent scientists to come and give a talk every Wednesday. The talks are aimed at undergraduates such that anybody can understand it, even the first year students can understand it. And so far we've had 4 talks and they've been all excellent, absolutely excellent. And we've videotaped them actually starting from the second lecture. And we're going to put them up on a website, but some, I mean, we always ask for permission from the speakers, and some speakers are not very comfortable putting them on the general web, and some are. So we will have to deal with things at an individual level, and some sites might need to be password protected and stuff like that. There are suggestions that we would now actually acquire the technology to broadcast them on things like Google Hangout or on the web. If I can do that, that would be fantastic. Whether we can do this for our regular lectures is another question. You know, that we need a little better infrastructure for that. But at least the seminar series and the kinds of what we have is we have the seminar series, and then after that we have a discussion, which is related, etc. And we can actually videotape a lot of that. And there's the physics league in the department of the students who are very enthusiastic about putting them all together. Putting all the slides together, as well as the recording all these talks, and how we actually disseminate them to the rest of the world, we'll have to think about, but it will be done.
I think you already know about that. IIT Madras and other IITs started this NPTEL, and they generally upload the lecture notes or the lectures, you know, the videotape and upload that.
That would be very good.
Probably, yeah, you can probably acquire their technology.
I think it depends on individual lecturers, and certainly this would be a wonderful thing to do. Yeah, I agree. I'll look at this.
Okay.
So I start again with the technical question. So, sir, your PhD thesis. So we are asking that approximately how many stars make a galaxy, and what is we don't know what is great attractor.
Well, I mean, the universe, in the universe, the basic the building blocks of the universe are galaxies, right? So it's like molecules in a solid. The basic unit is a galaxy. So there are matter is distributed in the universe in units of galaxies, and in each galaxy there are about 10 to the power 11 stars, right? 100 million. That's a typical galaxy, like our galaxy, the Milky Way. Of course, the galaxies vary in size. So there are dwarf galaxies that may have 10 to the 8 stars or 10 to the 7 stars. But they go up to about 10 to the 11, 10 to 12 stars, something like that. So these are the units of galaxies. Our galaxy is one of the big galaxies. It probably has somewhere between 10 to the 10 to 10 to the 11 stars, right? So these are galaxies. Now, you went back to my PhD thesis, which is, ancient history, but what we were studying at that time was looking at how galaxies move in the universe, right? I mean, the thing is that the universe is expanding, but galaxies are not all expanding with the universe, because galaxies pull each other, the gravitational force, and so as a result, galaxies have their own motions. There are galaxies that are falling towards each other. There are galaxies that are flowing, as we discovered in the 1980s, in coherent motion. And so there was a big discovery just before I started out my PhD, where a bunch of people, including my supervisor, Don Lyndon Bell, discovered that the whole surroundings in which our galaxy is embedded, the Milky Way, and surrounding galaxies, they're all taking part in a cosmic flow. They're all moving at a very fast speed. Our galaxy was moving, through the universe at about 600 kilometers per second towards a direction, and so were galaxies around us and things like that, very high speed. And of course, people were wondering what's happening. Why are there these coherent flows? Because at that time, people used to believe in a kind of cosmology where the universe was supposed to be mostly homogeneous on large enough scales. And so very large coherent structures, very large coherent motions were not predicted by this kind of cosmology. And so it was very odd to find that there were large flows of galaxies, and because galaxies have all these stars in them and they're all moving, including our own galaxy. So what this group had found in the 1980s was that our galaxy was going towards a direction along with various other galaxies around us, and they thought somebody is pulling us, and they named this object the Great Attractor, so that it attracts thousands and thousands of galaxies going towards it. And the quest then was to find this Great Attractor, and I was given the job of finding the Great Attractor. So what I did was, part of my thesis was essentially digitizing very large numbers of photographs of the sky, in fact almost half of the sky, and using a computer to automatically find galaxies in them. And then from these distribution of galaxies, trying to figure out whether in the direction in which we are moving, there is any unnatural or unusual concentration of galaxies that might actually be pulling us. And in the end, the bottom line was that there was no Great Attractor. We did not find one. But in the bargain, I found several very interesting things. And these were really large structures of galaxies. I, in fact, found the largest structure of galaxies that is known in the nearby universe, which I named after Shapley, which is called the Shapley supercluster. And at one point, I thought, well, I found the Great Attractor, because just in the direction of motion of our galaxy, we found that there was this huge structure of galaxies which consisted of tens of thousands of galaxies. But it turned out to be too far away.
Okay.
So, the bottom line of that chapter of my thesis was that we found this wonderful attractor in the direction of our motion, but I established that it was too far away for the gravitational pull to be strong enough to cause the motion of our galaxy. And but we, in the bargain, we discovered some really large structures, and of course, that completely conflicted with the cosmology then. Okay. And so slowly we discovered that there are all these very large structures that consisted of tens of thousands of galaxies all around us, and we call them superclusters. This whole subject of superclusters essentially took off from there, and now we know that the cosmology we believed in the 1980s was wrong.
Okay.
And actually, the universe is made up of a kind of dark matter and dark energy where large structures are possible. But this was discovered in a survey of galaxies where we were looking for something else.
Okay.
It turns out now that the Great Attractor, probably isn't there, and our motion, the motion of our galaxy, is actually a vector sum of the pulls due to different superclusters in different directions, right?
Okay.
So actually, there is nothing in the direction where we are moving. It is actually a result of various pulls in various directions. But that's how things turn out in the universe. I mean, it's not made up like that. But it was a very attractive thing for people in the 1980s to believe that there is this single big, I don't know, conglomeration of galaxies sitting there that's pulling our galaxy, and he wanted to find it out.
Okay. So, sir, if I have understood correctly, is the universe is, rather than what we thought is it's made up of homogeneous distribution of galaxies, but now we know it's made up of local lump of structures called superclusters or clusters, and within these clusters, and there are local motion, which which you observed in your PhD thesis or before that, right? And
yeah, I mean, let me show you a picture.
Okay.
This will explain this. Okay, so let me share a screen with you. Right. So, for example, if I sorry. Can I share a screen? Okay. Right. So can you see my screen?
No. Not now. Yes, now we can see your screen. Yeah.
Right. So here is a section of a photograph of the sky, right? And the blobs you see, this is a real photograph. The blobs you see are galaxies. Now, in the structure, you can make out that the galaxies are kind of aligned, and they form structures in there. But there is no way of knowing whether this is a three-dimensional effect, because you're seeing a two-dimensional sky, right?
Yes.
So to actually establish that there are these structures in the universe, large-scale structures, what you have to do is to measure distances to each of these galaxies and then make a three-dimensional map. So this is done. This is done now. And for example, if you, it's done in two different ways. One is to actually do simulations.
Okay.
So if you look at this, for example, this is the result of computer simulations where people take a large number of galaxies. So the top left-hand corner is a box where there are 10 to the power 8 galaxies, say, and they are embedded in their dark matter halos or whatever. And as time passes, you can see that the structure emerges, very large structures emerge, filamentary structures and wall-like structures. And the bottom right-hand box is what the universe looks like now. Okay. Now, this is what emerges from computer simulations, which involve gravitation, simple gravitation and nothing else. And those yellow dots in those structures are the galaxies. And the filaments that you see are essentially dark matter that you can't see with your eyes. But the matter is there. You can feel the dark matter. You feel the gravitational effects of dark matter. But you see only the galaxies, which are those yellow dots. Now, you can ask the question, this is a computer simulation. Is the real world like this? And it is. So, for example, if you look at this particular plot, this is an observational plot where it's a slice from a three-dimensional map of the sky, where each point, those red, yellow, green, blue points are galaxies.
Okay.
And so you can see that there is a scale bar there that says that's 1 billion light years. That's 1 billion light years across. So it's a very large chunk, and it's a slice through a three-dimensional map of the nearby universe. Okay, and you can see there's a huge filament, and this is in three-dimensional space that is 1 billion light years long. Now, 30 years ago, 20 years ago, people wouldn't have believed that such large structures exist. When I found the Shapley supercluster, a very eminent cosmologist did not believe that this could be a real thing. But now you can see these large structures exist. So what is happening now is that, so for example, this is our local supercluster. This is in a computer simulation. And see, this is, I mean, you can see that there is a little dot here called MW, the Milky Way. Right? Okay. So do you see right in the middle?
Okay.
Can you see?
It's very small,
You probably can't. But anyway, so I mean, all those little circles are galaxies.
Okay.
And they lie on these little filaments, these thin filaments, and they move along this like a spider web. The word that is used in cosmology is now the universe is a cosmic web, right? And so galaxies move on this web. They don't move like cars, they're gravitationally pulled along these threads of this web. The threads being made of dark matter, so you don't see them. And then the galaxies, what they do is they're born on the web, they're born on the filaments, and then they go and fall into these clusters where where the web threads or the filaments intersect. So the top left-hand corner of this plot is, for example, the Virgo cluster, which is the center of the local supercluster, which is called the Virgo supercluster. And so you can see that our galaxy is actually falling in towards towards the Virgo cluster. So in the 1980s, this flow that we were talking about actually is a flow along the cosmic web towards the nearest node in this web. That's what we feel is happening now, right? And so this is the kind of thing that that we are discovering now. We're discovering this through simulations, and also through actual observations, where we make real maps of the sky, then measure velocities of galaxies, and try to figure out where they're going. And what it is telling us is that the universe is not homogeneous at all, even on very large scales. On the largest scales, it's probably homogeneous, but it's very clumpy. And one of the challenges in astronomy now, it's a very young subject. I mean, astronomy, cosmology is a very, very young subject. And the challenges are to try and reconcile the fact that starting from a very uniform universe, we've come into a very clumpy universe. And then to figure out, how it got that way, right? And so that tells us a lot about the unseen components of the universe, of the dark matter and the dark energy that we can't see. So, for example, different forms of dark matter and dark energy would give rise to very different forms of the universe, right? In some cases, the universe would be very clumpy. In some cases, the universe would be very uniform. In some cases, the universe would be so uniform that the Earth and the solar system will not form, right? So the fact that we are here depends crucially on this evolution of structure in the universe. And that is what we're trying to understand now in a very real way.
Okay. So, sir, you mentioned several times dark matter and dark energy, and what we know, what is broadly known, is dark matter means it just cannot be seen, and it can pull things. So can you add some more words on what is dark matter and dark energy, and how dark matter is different from dark energy?
Well, there are two different things. Well, dark energy is a very new concept. Dark matter was known from the 1930s. When people realized that actually we don't see most of the matter in the universe, because you can feel it through gravitation. And only in the 60s and the 70s of the last century did we actually first make measurements of dark matter. For example, it was found that the outer parts of galaxies the stars in the outer parts of galaxies move with the same velocity as the stars in the inner parts of the galaxies. Which is, for example, is not true in the solar system, for example. Saturn and Jupiter move very slowly compared to the Earth. And that is because most of the matter of the solar system is in the sun. And so if you go to the periphery of the planetary system, of the solar system, things move much slowly. In galaxies, if, for example, all the matter in the galaxies were within the visible parts of the galaxies, you would have expected the stars in the outer parts of the galaxy to move slowly. And it doesn't happen that way. And so people then realized then galaxies are actually embedded in large halos of dark matter. And then people realized then you actually see only a very small fraction of all the matter in the universe, because they're in stars. On the whole, the universe is dominated by a matter that does not have light. And on top of that, from the late 90s, it was very obvious that actually the universe is not made up of matter at all. It turns out, because matter gravitates, if the universe were made up of matter, the expansion of the universe would actually be slowing down, right, starting from the Big Bang, because all the matter will pull it back. From the late 90s, it was apparent from the work of several groups that the universe's expansion is actually accelerating. So there's something that's pushing it rather than pulling it back. So then they realized the universe, 3/4 of the universe's mass energy, mass and energy are equivalent, right? E equals mc squared. So the universe's energy, 3/4 of it is actually in the form, not in matter, not of matter. It doesn't pull, it pushes. And so they called it dark energy as opposed to dark matter. And so that means that right now the universe's expansion is speeding up, right? So if you remember when Stephen Hawking wrote his book called The Brief History of Time, which was so successful, the last chapter is all about what will happen to the universe when it comes back. He was talking about, whether, cups that fall to the ground and break, will they actually come back together? Will everything go back in time? And, things like that. And that's already irrelevant now, right? Because we know that the universe is accelerating. It's never going to come back, right? Yes. And so this whole concept of dark energy changes everything. And that is why I say that the whole subject of cosmology and astrophysics is very young, because we are only learning about what the universe is made of now, and embarrassingly, we don't know. If you ask, I know what my table is made of, what I am made of, very well, actually. Yes. But I don't know what the universe is made of. Such a basic thing like that, right? And then come these terms called dark matter and dark energy. But if you ask me what is dark matter made of, I'd have no clue. And then if you ask me what is dark energy, I have no clue. I've just given these names, right? So this is going to be the subject of the 21st century, I think, for us to discover what the universe is made of. But right now, the only way I can actually do it is actually simulating, because I know that all these things interact with each other through gravity. Gravity is a very simple physical law that I can simulate in the computer. So people make these very large-scale simulations and try and figure out, how the universe might evolve. And slowly, as people learn more and more about the nature of dark energy, for example, the equation of state, of dark energy, stuff like that, we don't know. Once we know that, we will put them into these simulations and then figure out, whether we can produce the universe that we can see now.
Okay. So, sir, these things that this dark matter, dark energy, and how the observational astronomy is forcing us to believe in this, because we still don't have any theory or any theoretical belief or any theoretical understanding of dark matter and dark energy. These are all, at this moment, the observational astronomy says that there should be something and it should exist. Otherwise, the present laws of physics is not consistent. So, sir, if
dark matter, we have a good theoretical understanding. I think we do, because in the 90s, even in the 90s, people didn't know whether dark matter would be made up of light particles like neutrinos, or heavy particles like supersymmetric particles. But that question has been resolved, I think, because what people have shown theoretically is that if dark matter were made of light particles, then the universe now would have very large structures and very few small structures. And that is not true. The universe, the picture of the universe I showed you, had very few large structures.
Yes.
Right. And so that rules out what we call hot dark matter, which is matter that is made up of neutrinos. So we know that dark matter has to be made up of particles that are much heavier than protons and neutrons. Okay. But they are not particles that are made up of quarks. We know that because to some extent we know from Big Bang cosmology the total number of quarks that were made in the Big Bang. And that accounts for a very small fraction, about 1/5 of all the matter that there is in the universe. So we know that actually dark matter is made up of very heavy particles that are not like protons and neutrons, but they'll have to be. So these things we know, except that we haven't found these particles.
Yes.
So this is, this might be found in the LHC. It's not an astronomy problem. We might find them in the next round of experiments, and particle physicists will find them, right? So this is not the problem of just astrophysics. I mean, physics is the same everywhere, right? So some other branch of physics will find them. Similarly, dark energy might actually be something that people doing field theory or string theory will understand, right? Because we have no clue. I can tell you that this is how the geometry of space-time is affected by dark energy. I can make measurements and tell you that this is what I have learned about the acceleration of the universe. That is what an observational astronomer says. And then somebody has to make sense out of it. And this is where you come in. And people like you doing theoretical physics are going to actually do this.
Yes. So, sir, if a student, undergraduate student or a college student or just starting PhD student wants to know more about this astronomies and just know basic astronomy, know good astronomy or astronomical things. So, can you give us a reference, or do you have any article written by you, which is kind of semi-popular, which will motivate one to take research in astronomy and as well as give some qualitative and quantitative measure of what one should do when one is doing
Yeah, I
astronomical
mean,
research?
there are, I mean, there's quite a lot of, there are quite a lot of books and quite a lot of very good articles around, very good websites around. I can make a list of that and put it on your website if you want. I think
Yes,
that's the
yes,
best
that
way
will
to
be
go,
great. That will be great. If you just
rather than
send me,
my
I will
telling you what books
put
there
that
are.
in.
Yeah,
Yeah,
I think I can easily make a list for you
yeah. So,
with, I mean, there are very good websites that also tell you a lot about what's going on.
okay, so now we are now at the last question we have from one of our beneficiaries. He's
Mm.
Shubhodip. He we supported him in 11 and 12, and he's now doing his undergraduate from Narendrapur, Ramkrishna Mission Residential College, Narendrapur. He asks two very basic questions. He asks that you have extensively has done some projects with black holes. So, firstly, why it is black, and if it's really black, then how do we know its existence? And the second question is that whether the time flows slow near the black hole and what happens at the surface.
Okay, I'll give quick answers to these because I could actually spend the whole night talking about black holes. It is not a small subject. Right. So black holes are black because nothing can escape from them.
Okay.
Black holes are black because no light can escape. I mean, if you think of, let's think of a very simple system. Let's think of somebody who's standing on the earth and jumping, right? So what happens when you jump? You come back to the earth because the earth pulls you back, right? If you jump harder, you go a little higher up and the earth pulls you back again. Then you can launch a rocket. It will go up another few meters and then come back to the earth. So depending on what your velocity is, you will eventually come back because the earth pulls you back. Now, there will come a point where you will hit the escape velocity for a particular gravitating system, and then you can escape from that particular system. Now, this escape velocity depends on two things. One is the mass of the object, and the other is the radius of the object, the size of the object.
Definitely.
Now, so the combination of the mass and the radius actually dictates what the escape velocity is. Now, we also know for the last 100 years that there is a limit to the velocity that anybody can attain, right? Einstein told us that the velocity of light is the maximum. So what happens if there's a system for which the escape velocity is more than the velocity of light or the velocity of light?
Okay.
Which means that nothing essentially can escape from the object, right? So people thought, even in the Newtonian sense, before people knew about the maximum velocity of light or whatever, that that there would be objects that are so compact, right? So you can, for example, turn anything into a system from which nothing can escape, right? Because it's a combination of the mass and the radius. So, for example, I can turn you into a system from which, except that you will be very small.
Yes.
So black holes are a natural consequence of the fact that things collapse, stars collapse after they die, and as a result of collapse, a large amount of mass can end up in a very small radius, very small space, such that its density is going to be so high from which nothing can escape. So black holes are stars, for example. There are two kinds of black holes. There are stars which are so compact that the escape velocity is such that nothing can escape, so even light cannot escape.
Okay.
And there are another kind of black hole which actually is more than 1,000,000 times the mass of a sun, and there are things that are 1 billion times the mass of the sun. These black holes reside in the middles of galaxies. There's one in the middle of every galaxy. These are called supermassive black holes. There are two kinds of black holes that are of the order of a few times the mass of our sun, and the black holes that are of the order of 1,000,000 to 1 billion times the mass of our sun. And both kinds of black holes have the same property, that they're completely black, which means nothing can escape from them. Okay. And the second question was, how do you then find them? Of course, you can, in Bangla we say shak diye mach dhaka jay. So if you have something like a black hole there, which is so extreme, you cannot hide them, right? Because it has immense gravity. So the way you find them is you look at velocities of things around them. For example, the black hole in the middle of our galaxy has been discovered and its existence proved because we found that stars right around the middle of our galaxy are moving so fast that they are completing the orbit in 15 years.
Okay.
Whereas our sun takes 200 million years to go around the galaxy, we found stars near the middle of our galaxy which are going around as fast as so fast that they are going around the whole center of the galaxy in 15 years. So from that you can measure the mass of the central part of our galaxy and figure out there's a black hole there. Similarly, for example, if there's a star that is turned into a black hole, it will pull matter from its surrounding stars or surroundings, and what will happen is that this matter will fall onto the black hole, and as a result of going so close to a very strong gravitating system, it's going to get very hot. And when it gets very hot, by very I mean tens of millions of degrees hot, they will start emitting X-rays. They will start emitting ultraviolet light. And this is what we detect everywhere. We find stars that are very bright in X-rays, and you cannot explain any other process creating such hot gas, right, falling into a star. So you don't see the black hole, but you see the gas that's falling into the black hole, and as a result of going very close to the black hole, they become so hot, they become very bright. So paradoxically, in the X-rays, black holes are very bright. Not the black hole itself, but the surroundings of the black hole.
Yes,
right?
yes.
So that's how we discover them.
Okay, and then this next question was that does time
Oh, the time. And yeah, that's another thing. Very, very interesting consequence of the theory of relativity is that the passage of time is actually different for different people. So the concept, the feel for time, the concept of time is actually independent. That's what Einstein did. In Newtonian physics, time was absolute. So everybody in the universe had the same concept of time. They were embedded in the same time. What relativity does is actually shows that everybody has their own experience of time. It depends on where they are. So what happens is that if you look at something that's falling into a black hole, for the person who is falling into the black hole, it turns out that their clock becomes slower and slower and slower. Right? Actually, when they reach what is known as, actually the black hole has no surface, of course. What is known as the horizon of the black hole is what is known as the Schwarzschild radius. It's a radius at which, beyond which, nothing can escape. That is the horizon of the black hole. At the horizon of the black hole, time actually stops for the person who is falling into the black hole. Right? It slows down and stops. Whereas for the person who's falling into the black hole, it takes an infinite amount of time to fall into the black hole.
Yes.
And that's a very, very interesting. Of course, I mean, you can't fall into a black hole because you'll be torn into pieces before you get anywhere near. But the fact that the passage of time is so different for the observer as well as the person falling in is very interesting. And of course, it translates into in a very different, very different experiences for gas falling into the black hole, for example, and stars falling into the black hole and things like that. So when it is a very real problem, and so you have to work this out through relativity when you are dealing with black holes.
Thanks for explaining these things. Thanks once again. We had a brilliant episode, and we would like to say that thanks for being the advisor of Padakshep. In future, we will ask for your advice in different things, and we'll take your advice, and we wish you best with your department. We are hoping and we are praying that we will have a very good department, and we can go back. We can see presidency at the 1920s when we have very good physicists. Thanks for giving
Thank you
us.
very much, and thank you very much for doing what you're doing. I really admire the work that you're doing in Padakshep. I hope that your organization, becomes much bigger, and you do a very good job. And I'm very happy to be of any help that I can be. Actually, ask me.
Thank you, sir. Ananda, do you like to add some more words?
That's all. Thank you, sir.
Thank you.
Thank you.